so let's start with the discussion of quantum field theory. So, so the idea is the following. First, I will give an outline of axioms of local quantum field theory. Then we will discuss the example that can be done in all details, the example of one-dimensional quantum field theory of mechanics. And then we'll see what. And then we'll start from there. So it's really not the definition, not the complete definition in all the details, but that's the sort of framework, the outline of what it is structured. Again, we have to fix a space-time category. Once the space-time category is fixed, the data of local quantum field theory are the following. To a space-time manifold M, we assign a vector in the space which is assigned to the boundary. So to d-dimensional, assign this, and to space, to n-dimensional and minus one-dimensional manifold, we assign the vector space. So, so this maybe before proceeding with the definitions, let me first give an example that goes back to statistical mechanics. So, statistical mechanics on graphs. Or in statistical mechanics, statistical physics, these models are known as lattice models. Because the graph is usually a lattice, kind of crystal lattice, and usually these models describe some atomic fluctuations or some thermal or electric properties of atomic lattices. So let's first, what is the space-time? Well, in this case, this is the category of graphs. Objects are finite collections of points, well, simply finite sets, and morphisms, well, you have one object, you have the other object, and then they are connected by a graph. So, composition is gluing of graphs just like this. And the assumption is, although it's not necessary, that gamma has no one-valent vertices except these endpoints. As I said, it's not necessary, but it's just somehow for aesthetical reasons. Okay, so So now let's let X be a finite set. So what we want to do is we want to define a certain model in statistical mechanics on graphs. So and it goes like this. So what I will describe are vertex models in mechanics. So first, states in such model are functions sigma from the edges of the graph to x. So to each edge we assign an element sigma e from x. So then weights, local weights. These are weights of vertices. If you have a star, so let's say that V is a vertex in our graph, and consider a star of this vertex, in other words, the collection of edges that are coming into the graph. So to the vertex we assign a function from x to the edges of the star of the vertex. So this is the star of the vertex. Two non-negative numbers. So basically it assigns. So if it will enumerate edges, then it assigns to this collection of states on the edges the number W V sigma E1 sigma En. And then the weight of the state sigma on gamma W sigma is just a product over vertices WV of well, sigma SE. That's the sigmas on the surrounding edges. Okay. And then we have the probability distribution. So this system of weights, these are non-negative numbers. So it defines the probability of a state on graph gamma given by yes. So then sorry, it's too big. So then edges of gamma we will separate into two groups: inner edges and outer edges. So these are the outer edges, the ones that are sticking out, the ones that are adjacent to one-level vertices. So a state sigma on gamma we will write as sigma inner and sigma outer. And now let's fix sigma out, then we have the conditional and define the conditional probability of having sigma inner as probability sigma inner sigma outer 1 over z gamma sigma out, and then product over all vertices just W sigma. And this is the normalization factor, which normalizes probability to 1. It is given as sum over sigma inner W sigma. And this is known as the partition function. In statistical mechanics, and one of the main problems in statistical mechanics is to analyze the asymptotical behavior of these partition functions when the graphs are increasing. So, for example, when a graph is planar and when it's just part of the square grid that is inside of some domain in R with the step epsilon. So then this is an example gamma epsilon, and then you take the limit as epsilon goes to 0, the number of sides increases, and then there is a whole subject. So this is the thermodynamical limit in statistical mechanics, and these are the most these are the questions that people are interested in statistical mechanics, and not only in asymptotics of the partition function, but more generally, this is a probability distribution on this space of states on such graphs. So the question is how the whole probability distribution will behave in this limit. And it's a very interesting subject, but as you can see, it belongs more to analysis than to algebra or geometry. But the core structure here is two things: this partition function and this probability distribution. And so let's just focus on the partition function, and let's focus on its properties. So suppose you have two graphs that you want to glue together. First of all, let's look at the structure of this Z gamma. So we can think of this Z gamma as follows. Let's define H of D gamma as Rx to the tensor power the outer edges. Rx is the direct sum over all sigma in X. Sigma. It's just a vector space where elements of the set X form a basis. Right? So then it's clear that Z gamma can be thought as an element of H d gamma. So z gamma then is sum over sigma outer. Well, let's enumerate. Let's say that outer edges are enumerated E1, En. So then this is sum over sigma 1, sigma n, z gamma, sigma 1, sigma n, and then sigma 1 tensor sigma n. So sigma, in this case, sigma is a basis in Rx. And so it's a vector in Rx n times Rx. And we should, because we choose the enumeration of outer edges, this is exactly Rx to the outer. Is it clear?
You have somehow changed the notation along the way.
Hmm?
Sigma was originally a map from E gamma to X, and something funny here.
So let's call it X small. Okay. So then this is sigma. Yeah. Okay, sorry, I was
Yes.
E1 sigma En. And that should make sense.
Right. That's better.
So what are you summing over?
What?
What is it you're summing over? What
I'm summing over
different
maps.
states? Oh.
Yeah. These are the maps from outer edges E1, En to X.
Right. So you're summing over sigmas. It's only
Over
sigmas.
sigmas, yes.
Right.
Yes.
Okay.
Mm-hmm.
Right. So.
Which is the same as well, by the way, it's the same as I would write z gamma as.
So is sigma only defined on the outer edges or on all edges?
The arguments of z gamma, the argument of z gamma, it's defined only for outer edges.
Okay.
So z gamma is, it's like this. We have outer edges, and we put on them states sigma E1, sigma E2, sigma En. And for outer states which are fixed, we define this partition function as sum over states on inner edges, and then the product of weights.
So it's all X colorings of the outer edges.
So sigma is only on out.
This one?
Yes.
No, this one on all of them,
Or
but then I
okay.
split it into two parts.
But it's just the coloring of the outer edges, right?
It's just the coloring of the outer
With
edge.
with X.
With X, yes. Okay.
And there could be some multiplicities that's maybe ignored over there. But
What do you mean multiplicities?
well, I mean, it depends if you choose the sigmas as maps on all edges. Because I mean, for a fixed sigma out, the same sigma out could be a part of a lot of sigmas, right? There could be a lot of sigma n's. That
No, for each edge you have a color. Just
No.
one color.
no. For
Yeah,
each coloring, your edge has a color.
No, for each edge have an element of x.
Right, given a sigma. But we're
That's-
summing
that's-
over different
well,
sigmas,
no,
right?
that's what sigma is.
Sigma, yeah, right. So we're summing over all sigmas, right?
No.
And then I'm summing
When-
over all sigmas.
Right, all sigmas. But then there's multiplicities if you only look at sigma out, right? Because you can have the same sigma out as a part of different sigmas. Right.
No, let's do it like this. You fix sigma out, and then you're summing over all sigma inner.
Then there's, I mean, so how? Then there really isn't any sum, is there?
So then z gamma is given by
Oh, like that.
Yeah,
Okay.
yes.
Yeah.
Oh, so okay, so
And then I'm assembling.
so you're basically just taking the multiplicity of sigma out. I mean, and then counting the number of times sigma out
Yes, you can.
can
you
be a
can
part of
think
a sigma.
You can think of this as the number of weighted number of states on the inner edges. I think that's what you call multiplicity. So what I did here, this sum is just a sort of rearrangement of these numbers into one vector, where the numbers are components of
Oh, I
this
see.
vector.
Okay. Yes.
But okay.
You see, here we have the bunch of collection of numbers, and here we use these numbers to define a vector where the components are given by those numbers.
I still don't fully understand I mean the in which order you determine you take things. So you take a graph and a set x, right? And up there you assign to a coloring of the outer edges of the graph. You assigned a number up there,
Yeah.
right? Okay. But now you fix that coloring of the outer edges on the graph,
Well, in this sum it is fixed,
right?
but then you can
But
vary.
okay, so that C gamma is the same C gamma.
Yeah.
So that's still with the fixed coloring of the outer edges.
Well, you see, z gamma is a sum where this coloring is fixed. But then you take the direct sum, you assemble these numbers. For each outer coloring, you arrange them into a vector, where the components are given by those sums. Let's look at the example. Say, let's look at this graph. So we have 4 edges. So in this case, it's just given by the weight of one vertex. Right? All edges are outer edges. So in this case, z gamma is just sum over sigma 1, sigma 4. Now I'll write x1, x4. Z gamma x1, x4, x1, tensor x2, tensor x4.
What is x1 up to x4?
Sigma.
But didn't you fix those sigmas? So that's the part I don't understand. Didn't you fix those sigmas? Didn't you fix the coloring of your? Right.
To define this number, I fixed it.
Okay.
But then, this is the, well, this is, but then I use these numbers to define a vector. You see, this is not the sum of numbers. It's the arrangement of these numbers into a vector.
Oh, I see. So you are summing over all colorings of the outer vectors.
Yeah,
I mean, because yeah. Okay.
yeah. This is a basis. And these are the coordinates in this basis. So in some sense, this summation is just like, it's the arrangement of those numbers into components of a vector. Is it clear?
Yes. So this is the, so you can see that
it gives the data, what I just wrote over here. But now let's look at the properties of this vectors. So can I erase all this? Is it more or less clear? So let's look at the spaces. So outer edges, they are in bijection with these endpoints. So if we have E out as the disjoint union, E1, E2. So then what do we have for this vector space? Vector space assigned to E out. In this case it's Rx to the tensor power E1 disjoint union E2. One can naturally identify it with the tensor product of vector spaces. So it's equal to H E1 H E2. Agree? Okay, so this is the first property. Second property. Suppose that gamma has no, so what do we assign to an empty space if there are no outer edges? This is just R. So then nothing happens. 3. Suppose that gamma is equal to the disjoint union of two graphs, so that you have gamma 1, gamma 2. Then if you look at this Z gamma, Marcel, do you have a question?
No, I'm just wondering, E1 and E2, are they disjoint?
Yes.
There are no strings passing all the way from upper to...
What do you mean?
I mean, in this picture, there are no edges passing all the way from the upper to the lower.
Oh,
E1 is also connected to the upper boundary. I think, if I got it right.
Well, we could just put in a vertex in the middle, for instance.
it doesn't matter.
Okay.
And that's a way of making those disjoint, right? I mean,
Yeah.
so we allow two variant graphs in the middle, for instance.
Yes.
So we just put a vertex in the middle, then we have split that.
Yeah.
Ah, yes. Oh, okay, now I understand. Yes. If you have such thing, and if this has just weight 1. So if so you put any color here, and you can put as Malik suggested, you put a virtual vertex here such that so its weight is 0 if the colors are different, and its weight is 1 if the colors are the same. It's like the identity matrix. So x1, x2. The weight of this is delta x1, x2. Okay, so now, so what is this thing? Well, I just, because we have to make a break now, so I claim that this is Z gamma tensor Z gamma.
No, you have 15 minutes.
15 minutes.
15 minutes.
Oh, I see. Good. Sorry. So then, let's look at this expression. So in this case, me first make a statement. So this is an element d gamma 1 h d gamma 2, and I hope this is clear. So then, if this is the disjoint union of graphs, then the outer edges they split naturally into the disjoint union of two sets, the outer edges of gamma 1 and the outer edges of gamma 2, and these products, so then Z gamma 1 disjoint union gamma 2 of sigma, I will just write it like this, sigma gamma 1 sigma d gamma 2, it's sum over sigma inner on gamma 1, sigma inner on gamma 2, and then the weight sigma gamma 1 inner, the weight sigma gamma 2 inner. And the reason for this is that if this is a vertex from gamma 1, its star will always be in gamma 1. There will be never vertices from gamma 2 attached to gamma 1 because the graph is disjoint. And this is why the weights will be the product of weights, and that's why the vector will be the tensor product of vectors. So this is the, now is it clear or not? I hope it is. So this is the second property. And finally, so this is the third property. So finally, let's look at the case when you have two, well, say when you have a graph gamma, say even more general case, you have a graph gamma, you have some set of edges here, d gamma prime, you have another set of edges, d gamma 1, and then you have another set of edges here, d gamma 2. And then let's assume that F is a bijection between one finite set and the other. This is F. Using this F, you can connect edges from this collection to the edges of this collection. So you can sort of close these outer edges and turn them into the inner edges. So before we'll proceed with this picture, just one more property I should have, well, yeah, I'm sorry, this is number 5. I forgot about number 4. I will continue with the number 5 property. So, property number 4. So we have a vector space H that we assign to the boundary of the graph gamma, which is Rx to the tensor power this set the boundary of the graph gamma. But you see, by definition, this is a vector space with a basis. So it has a basis. Simply the with monomial basis. Because it has a basis, it has a natural scalar product. It's Rn. And here I want to make a remark. So far, this construction was non-oriented. But one can consider, oriented graphs. In other words, edges would be oriented. And then this pairing would be between H d gamma with the opposite orientation and H d gamma. And in quantum field theory, we will consider the case of oriented manifolds. So this will be, so we'll have the version of this pairing. Okay, so now the continuation of the fifth property. Now we have a bijection between these components. And now let's look at our partition function z gamma. So z gamma is a vector in h d gamma, but this h d gamma is naturally a tensor product d gamma prime tensor h d gamma 1 tensor h d gamma 2. We have a bijection f between this component of the boundary and this component of the boundary. So f induces the natural isomorphism of these spaces. It just permutes the factors in the tensor product if necessary, so that they would match. Linear isomorphism. Okay. So if we'll apply this linear map to z gamma, we will have a vector in h d gamma prime tensor h d gamma 2 squared. But then we can take the scalar product of these components. So what we can do is, we can take now apply this to z gamma. Z gamma is 7. And this will be a vector in h d gamma prime. Okay, so just using this pairing, we constructed out of z gamma, using the pairing and using the identification of d gamma 1 and d gamma 2, we constructed a vector in this space. But we have another vector in this space. We also have z gamma f in this space, where gamma f is the result of gluing d gamma 1 to d gamma 2 via this, using this identification f. So it just, you glue those edges to these ones. You will get another graph, and using this construction you will get another vector corresponding to this graph. And then the exercise for the lunch before the afternoon is to prove the following theory. These two vectors are the same. Applied to z gamma is equal to z gamma f. So there are 5 properties that these partition functions tautologically satisfy. It's just an elementary linear algebra in combinatorics to see that they hold. And then the important kind of philosophical consequence of this is that, I mean, if you're really optimistic about computations, then you can say the following. Well, this is really a great collection of models in statistical mechanics, in the sense that I can assemble all partition functions from the partition functions for very small regions, just by gluing these regions together. And of course it's encoded in the very definition of these models as sum over weights, and the weight is the product of local weights corresponding to vertices. So in some sense, the most elementary partition function is when you have a vertex and then edges around it. And then from these partition functions you can assemble all others. And that's the idea of locality. And so this, and if you think about these axioms, so basically this axioms tells you that, so far, I'm sorry, these are not axioms, these are properties. There will be axioms for local quantum field theory. So if you look at these properties, you can see that basically what they guarantee is, they guarantee exactly this, that you can chop up the space-time into very small pieces, and then you can glue the partition function for the bigger piece from small pieces. So, okay, so this is an exercise for the afternoon lecture to prove that this is the same. And then basically what I will start the afternoon lecture by saying that we have these natural properties for statistical mechanics, so we will just axiomatize them and we'll make them into the axioms of local quantum field theory. And we'll see that quantum mechanics also satisfies the same properties. And then we'll start to construct other examples using basically this idea, except instead of the sum, we will have some kind of horrible integral, and the main goals of all this is to make sense of such sum when instead of the sum you have the integration of all fields. Okay, so